I know. Okay. So yeah. So what I'll do is I'll do some quick. I have some slides which I will quickly go through. So nothing new, nothing different from what you see in the lectures or what I have added in the document for 7 to 12, right, as notes. In fact, it is more of 7 to 10, not really 7 to 12. So I just go over them. Few changes I've made here and there. So I'll probably mention those changes, and I'll also talk about what are the key things you have to know and along the way. Okay, so mainly I'll do statistical learning theory only. So the privacy is, as I told before, right, it's just those two lectures, and as long as you know what is there in those two lectures, we won't go too much beyond that, right? So that part is not going to be very hard. So that is I've mentioned that part already. Okay, so 75% roughly 75% will come from the last 6 weeks, meaning 7 to 12. You'll have about 75% of the marks, not the questions, marks, right? So when it comes to marks, 75% will come from the last 6 weeks. About 65% will come from just statistical learning theory alone. Okay, so I hope that is clear. So 7 to 10 is like what we are mainly testing in the end term. And of course, some 25% you'll have, which comes from the first 6 weeks, till from starting from simple probability inequalities to JLMA, LSH, spectral clustering, randomized SVD will cover about 25% in terms of marks. Okay, so 65%, as I said before, will come from this topic, statistical learning theory. So I'll just quickly go over that. Uh, so nothing new, as I said before. It's just stuff that you're supposed to know. So please think of this as a refresh. Okay. The first thing that you'll have to know in this in these 4 weeks is the idea of a joint distribution. So that is very critical. There is a joint distribution over the features and the labels. Okay, so typically we deal only with classification problems in our course, only binary classification, that too. So y will just be 0 comma 1, x will be some feature space, so some d features will be there. So you have a joint distribution governing the features and labels. So this is an example that you can keep in mind. Okay, so these are all multivariate normal distributions, but you can just think of them approximately as some densities of x given y. So these are two different class conditional. So we call them class conditional densities because you're conditioning on the class which is either 0 or 1. Okay, so one formula or one relationship which is going to be very handy is this decomposition of the joint probability into this marginal over y and conditional x given y, right? So this is a extremely useful form. So this is what professor calls the generative story, right? This is one way to think of a generative story for the joint distribution. So you first pick the label, and then you, given that label, you choose one of these two densities and you sample a point x. Okay, so you can think of it that way. You should also be aware of the other way of looking at it, which is you first, this is also equally valid. So you first sample from the data distribution. Okay, you have a distribution over the features, and then you give it a label. Okay, so you can think of it in both ways. Depending on the problem that is given to you, one of these might be more suited. Okay, so what you have to remember is the label. You could have the same data point. For example, let's say you have two features. Okay, uh, and there is a label corresponding to it. So you could have the same feature vector, let's say x1 comma x2, but two different instances where the label in one case is 1 and the label in the other case is 0. Okay, that is entirely possible. That is because there is randomness over both x and y. Okay, so it's, you could have the same data point repeated in terms of the features, but having different labels. Okay, you should not get confused. So it is not as though the the labeling is unique in some sense, right? So it is not unique. So there is this randomness guarantees that you could have different labels for the same feature vector. Okay, so that is one possible confusion that might be there. I'm just making you, so you might be aware of this, but in case you are not, please make a note of that. Okay, so the next point which is very important is to realize that the training and the test data both come from the same distribution. Okay, this is a very critical assumption. This is what makes learning possible. Okay, so in a practical situation, there are extremely interesting situations which you encounter in practice where this is not true. So for example, so this is called at some data shift, right? So you have different terms. So the distribution could shift. So in a simple example is your distribution over the data features might shift. You could have trained on a certain set of images, okay? But when you're testing, the images that come to you may be very blurred, okay? So the distribution over the images may change, or the data may change, or the distribution or the label space itself might change, or the relationship between the features and labels might change, okay, in a practical situation. But we are ignoring all that. What we are assuming is the distribution of the feature label pairs that you see during training is exactly the same as what you will see when you're testing your algorithm on some test data. Okay, so this is a critical assumption that you are making. So that is regarding the joint distribution. So this notation is also important. So what this means is that you are sampling n data points independent and identically, so from the underlying distribution. So we use d power n in this case. So this is the notation. There are n data points and you call them x comma y belongs to 0 1. Sometimes it may be -1 comma 1. That will be made clear in the problem statement. Okay, so you don't need to worry about that part. But typically if nothing else is mentioned, you can assume that the label class is set containing 0 and 1. Okay, so this is mainly what you need to know about the joint distribution. The final point regarding this slide is you have to understand that all the randomness that we talk about comes from this place. Okay, so strictly speaking, we don't discuss any randomness concerning the algorithm, learning algorithm, right? So all the randomness comes from the data distribution. All the probabilities that we compute, all the expectations that we compute are all over the data distribution. Okay, so whenever you see expectation, if there is no, if the distribution is not specified, then you must assume that the expectation is computed over randomness in the data generating process. Okay, so that is regarding this slide. So yeah, now we always use H for the classifier in these weeks, and the train error, test error, you already know. So I'm just quickly going over it. So we won't say what is the train error in the exam, what is the test error. If we use these notations, you must know what we are talking about, right? So this notation will be very faithful to it during the exam. So RSH means train error. It's the average, it's a 0 1 error. So on an average, how many times do you misclassify, right? So it's the misclassification error. And the test error is, there are two forms, both are very important. Okay, so what is the test error telling you? One thing it's telling you is how likely are you going to make a mistake, okay, on an average, when you take the average over the entire data distribution. Alternatively, you can think about it as the expectation of the indicator random variable. Okay, so this form particularly is very useful, as we will see. Okay, so especially when in computational problems, when you're asked to compute things, you should go for this and not really this. So they are the same, but if you put it this way, then life becomes easy. Okay, and as I said before, this all the randomness comes from the underlying data distribution. So the base classifier and base error. So the base classifier is what? The best possible classifier across all possible hypotheses that you can think of, right? So so you're not restricting the hypothesis class here. So this is like the best possible binary classifier for the given problem. So the one that minimizes the test error. Okay, so when you're discussing about the base classifier, there is no notion of learning algorithm at all. Okay, so you're not learning anything here. You're not even talking about learning. So all that you care about here is the optimal setting. Okay, so there is going to be some optimal classifier. What is that? That is all we are concerned with here, and not really learning. So okay, so that is the base classifier. The error of the base classifier is the base error. So you already know these two. Now, how do you compute it? So you can actually show this. We haven't proved this formally in the course, but if you define the base classifier in this way, then it turns out to be the one where this conditional probability is greater than 0.5. Okay, greater than or equal to 0.5. So uh, that is what. So this is actually not non-trivial. Okay, so you have to show this. You have to formally sit and prove that if this is how you define the base classifier, then it turns out that this is what the base classifier is. Okay, intuitively, of course, as the prof mentioned, this is quite clear. Whenever you expect the probability of 1 to be greater than or equal to 0.5, then that should mean that that is what you have to output. But then you still have to prove this, and we haven't done that in this course. Okay, so once again, I want to stress this fact that what determines H star is the underlying distribution D. Okay, and not the learning algorithm or anything of that sort. So practical setting, we of course don't know D, and if you know D, then there is no point of learning, because you can as well estimate H star and be done with it. Okay, so this is there in the notes. I'm just repeating this. So, but it's important. So what you are doing is, this is the condition for the base classifier, right? So if you can find out where y equal to 1 is more likely than y equal to 0, you are done. So what you do is this. The Bayes theorem kind of allows you to flip the conditions. So y equal to something given x becomes x given something, x given y equal to something, right? So what you have done is you have moved from this to the class conditional densities. Okay, and that's very convenient. So now what you can do is, if you go back to that original generative story of first choose y and then pick x, then if you're given some situation like that, all that you need to do is look at the class conditional densities and see where one is bigger than the other. Okay, so in the assignment and in the notes, I have given a particular example where these two are equal. Okay, so the prior probabilities are equal. If that is the case, then this becomes very simple. All that you need to do is you need to see where one curve crosses the other. Okay, so there will be a point where, so this is like the density, class conditional density for class 1. This is for class 0. Wherever it crosses, you just make a note of that. That is your theta. So here green is above red, so you output green. Here you output red. Okay, so this is for a particular example. I want you to please make a note. This is not always true. Okay, so if this is different, for instance, if maybe say there is a greater chance of points coming from class 1, right? So maybe let's say this is 0.7 and this is 0.3. Then this line will shift. Okay, so this line will not just be the point of intersection of these two curves, but I guess it will shift to the right. Okay, if P of y equal to 1 is bigger, then it will shift in one direction. If P of y equal to 1 is smaller, then it will shift in the other direction. So you should not blindly go by this example here. Okay, however, this is true. This is always true. Whatever we have done here, notice that we have not plugged in these two to be equal. Therefore, it is always true. But then this example, particular example of this line coming in between, separating these two, you have to be careful. Okay, this is only true in a specific situation mentioned here. Okay, so that is with respect to computing the base classifier. You must know then the base error, of course. So this is where I mentioned the expectation is easier. Expectation of the indicator random variable is easier to deal with. compared to just thinking about it as a probability. So what you need to do is you have to expand this expectation. Okay, and this can be hard or easy. So what I have shown you here is for uh, continuous class, so a continuous random variable. So if your x is continuous, then this is the form you have to deal with. So y is anyway discrete. So y is like 0 or 1. So this part will stick. This part will not change. But this, depending on whether your x is discrete or continuous, will change. So in, I think, last exam, in the end term of last term, this was discrete. So what you have to do in that case is change the integral to a summation. Okay. So again, the going with the example that we discussed earlier, what this will mean is, so see, you have to look at p of y equal to 0, right? So, and to start with, y equal to 0 is what? This red color curve. So in the red color curve, you'll have to ask this question: where is, so this integral? Remember, is over the entire region, okay, over all the real line. So it's not limited to a particular region. The reason I have shaded this here is the indicator will become 0 in a particular region. So for example, here the indicator is 0 because it's not misclassified. Okay, so this area is not really needed. So this area will not be counted because the indicator will collapse this entire integral in this region. Let's call theta, say 10, right? 10 to infinity, this will collapse for the first integral. Okay, so the part that will be active for the first integral is this region. Okay, likewise, this integral is over the entire real line. The part that will be active for classifier 1 is wherever there's a misclassification. So you have to focus on the mistakes. Okay, so here there are no mistakes here because it's anyway predicting it correctly. It is only this region which matters. Okay, I hope this distinction is clear. So the integral is over the entire region, but because you have an indicator function, you are only concerned with those parts of the real line where there is a mistake. Okay, so this is for a continuous random variable. For a discrete random variable, the formula will change. Okay, so this, as I mentioned before, the integral should be replaced by summation. The summation once again is over the support of x. Okay, so for example, I think in the last n term x, there were four values. I think 4 points on a unit square. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so therefore you had 4 values to sum up. It could be more, it could be less. Okay, it depends on the support of x, meaning wherever this is going to be positive, right, and or rather non-zero. So that is what you have to keep in mind. So there, here this will be replaced by the mass functions and not the densities. Okay, so as far as computing the base error is concerned, these are two main things you have to keep in mind. Expand the expectation, and depending on whether it's discrete or continuous, use a summation or an integral. Okay, and focus on the regions where the classifier is making a mistake. Okay, so that's because that is what is going to be non-zero. Okay, so that is concerning the base error. So now, only now the algorithm comes in. Okay, learning algorithm. So far you didn't have any need for the learning algorithm. So what is the learning algorithm? So first of all, you start with the distribution. You generate a data set, okay, in an IID manner, and you have to feed it to the algorithm. So you don't just feed the data set, you also feed the set of classifiers you are going to learn from. Okay, so because you need to restrict your hypothesis class to something manageable if you want to learn. Okay, so you feed both of these things into a learning algorithm, and the learning algorithm is going to output some classifier from its from H, right? So from the space of possible classifiers, it's going to pick one, and that is what we call Hs. Okay, so for some time, what exactly the learning algorithm doesn't matter to us. You treat it like a black box. So we are actually agnostic to the exact learning algorithm. All that we care about is the fact that there is some algorithm that's going to take the data set and the hypothesis class and output some Hs. Okay, that's all we care about. We don't care about exact nature of a, until we reach estimation error, we don't care about this. Okay, so yeah, so this is like again important, you should already be knowing all this, but I'll just repeat this. So RSHS is your train error. Okay, train error of your classifier HS. Now this is a random variable. Okay, so this part you have to be clear about what is a random variable and what is a constant. So when I say constant, it is some deterministic number. Okay, not a random variable. So all these four values are real by the way. Okay, they are not vectors, they are all scalars. But then the first two are random variables, meaning as you change, as you sample a different set of data points, you will get a different HS, you will get a different train error. Okay, so it's random. As you sample different set of data points, you will get different HS, therefore different test error also. So both of these are random. But this is fixed. So this is what? This is the best possible hypothesis or best possible classifier from the hypothesis class you have chosen. So this is fixed. Okay, this is also fixed. This is the best possible classifier overall. So where there is no restriction on H. You can think of this as some kind of an unconstrained setup, and this is a constrained setup. Okay, so these are the four errors, and their combinations will give us the three types of errors, right? So what we call generalization, estimation, approximation. So what are we trying to do is the following. So see, on the left is the only error that you have a handle over. Okay, this is the only thing that you can measure in a practical setting, right? So this is all that you have access to. This is what you would like to go towards. Unfortunately, you don't have access to this. Okay, so that is why we are measuring the difference between these two and trying to see how close one is to the other. So that is the reason you have this on the left hand side. Now in the decomposition, this is giving you what is this telling you? As the prof mentioned, all this is telling you is how close the train error is to your test error. Okay, so this is not telling you anything about how good the classifier is. All that it tells you is the closeness of your train error to your test error. How good is your train error as a proxy for your test error? That's all this is telling you. The rest of the two errors are all about test errors. So if you notice, there's an RD sitting on all four places. Okay, so this is all about test errors. So this is telling you how good is your classifier output by the learning algorithm. How good is it compared to the best possible classifier in your hypothesis class? And this is telling you this is the final classifier. Sorry, this is the final error, or rather, this is the only error that talks about the goodness of your classifier as far as the gold standard is concerned. So this is the gold standard. This is the only guy who is talking about how good it is in terms of your best possible classifier. Okay, the other two, in fact, are not at all concerned with that. Okay, so the other two do not control the goodness of a classifier in an absolute sense. Okay, the last one, the approximation error, is the only one which can tell you how far you are away from your ideal situation. Okay, so this is with regard to the three errors. And then you have your whole idea of uniform convergence. So what is this telling you? So you have RS HS. Okay, now to keep things simple, what we do is we start with a fixed H. Okay, we for the moment forget about HS. HS is what? The classifier returned by your learning algorithm. Okay, you forget HS for the moment and you consider H in general and you ask what is the relationship between RS of that and RD. So what you see is, on an average, the train error is a good approximation for the test error. Okay, on an average, if you take the expectation, then it is equal to the test error. Okay, so what matters here, of course, is the variance, right? So you could have two random, you could have a random variable. Remember that this is a random variable, and this is the mean of the random variable, right? The population mean or the true mean. So you could have a random variable which is whose expectation is equal to the actual value, true expectation, right? That is possible, but then there could be a lot of variance. Okay, so that is what we don't have control over at this moment, right? So by just saying that the expectation is equal to RD, all that we are saying is that this is an unbiased estimator of RDH. Okay, the train error is a very good estimator in the sense that it is unbiased. So on an average, it is the test error, but then average alone is not enough. How does it vary around the average? Okay, so that is why we need the concentration inequalities from week one. Okay, so the concentration inequality that's coming to our rescue is Hofding. So uh, one point you have to notice, there is a small error, small typo in the lecture notes. So this Mr. Nagarajan had actually mentioned earlier on. So this is that. So this is 2. There is a 2 missing. Okay, so in the lectures, it's actually the absolute value. Moment the absolute value comes in, you need to have a 2 sitting in here. So the 2 is missing, but that is the only typo. So otherwise, nothing else changes. So please add a 2 here. Okay, so that's Hofding. So Hofding is telling you that for a fixed classifier, the train error is close to the test error. Okay, and as the number of data points increases, it's going to get closer and closer, right? So you can have a smaller epsilon. So that's what it's telling you for a fixed H. Okay, this alone is not enough. You need the union bound also. So what that union bound brings in is it connects. So this is what we wanted, right, in the beginning. So this is what we wanted to bound. So it's going to connect this with this. Okay, so and what you end up with is called the uniform convergence result. So what this is telling you is there are 2 parts to it. So first you fix some epsilon and some delta. Okay, so what is the role played by epsilon and delta? So the role played by epsilon is how close you want your train error to be to your test error. Okay, so this is how the quality of your approximation or sensitivity of your approximation. So if epsilon is 0.1, then the train error is close to test error with a margin of 0.1. Okay. Now this is, by the way, these are all random. So remember, this is random, this is also random. Okay. So you can't talk about this in an absolute sense. So you have to therefore talk about the probability of this happening. Okay. So this is a random variable. You're talking about the difference of 2 random variables being greater than or equal to epsilon. So you can't just talk about that quantity alone. You have to talk about the probability of this happening. Okay. So as the prof mentions, this is a bad event. So how often does this happen? That is controlled, or that is on the right hand side bounded by delta. So you want to bound that by delta. So how often do you want this bad event to happen? Very small probability, right? Say 0.1. Okay. So the probability that, so what is this telling you? This is telling you the probability that the train error is a bad proxy for the test error, okay, is small. That's what this is telling you. Okay, but when will this happen? So that's the other part. So that will happen when you have enough number of samples. Okay, this is not always going to happen. So if you for a moment forget this, then the theorem is not really true, right? So what this is telling you is, provided you have enough number of samples, which is governed by this quantity here, okay, which is called the sample complexity. If you have enough number of samples, then the train error is a good proxy for test error. Okay, and as n tends to infinity, what happens is this becomes a better and better proxy for the test error, the train error. Okay, so that is what this is telling you. Now, what else should you know? I think, yeah, this is yeah, the other part is uniform, right? So what does uniform mean? See, uniform means that this holds for every single classifier in your hypothesis class. Okay, so it is uniformly true across all classifiers in your hypothesis class. So that is what is the speciality about this result, right? That's why it is called uniform convergence. So it's not true for some fixed classifier alone. For every single classifier in your hypothesis class, this holds good. Okay, so that is uniform convergence, and then this happens when you have at least these many samples. So that minimum number of samples is what you call the sample complexity. Okay, so all this is true for a finite hypothesis class, but unfortunately in practice we deal with infinite hypothesis class like linear classifiers or deep networks, right? So we need it will be great if we have a result that works for infinite hypothesis classes also. Okay, so that's where we are. So that brings in the whole idea of the complexity of a class. So how do we measure the size of a class or how complex it is using this idea of VC dimension? So what you need to know here is the effective number of labelings. So that part you need to know. So if you have n data points, you have 2 power n possible labelings, but provided you bring in, some restriction on the hypothesis class, the effective number of labelings comes down. So you must know that. So that part is important. So yeah, so for these are, so these things we will not specify in the exam, right? So for example, we will say h int and we will leave it at that. So we won't say what h int is. So whenever you see h int, you must know that it is the class of hypothesis class of interval classifiers. The other part we won't mention is that this is like a closed interval. So all these things you have to remember. Okay, so this is like open, closed interval, not an open interval. So that part you have to remember. uh, Axis parallel rectangles again. So sorry, the screen is not visible, right, anymore?
No, it's not visible.
Yeah, once again, I don't know what happened. It's going fine, suddenly it stopped. Yeah, sorry. I hope it has come back now.
Yeah, it's back, it's visible.
Yeah, so for where are we? Yeah, for axis parallel rectangles, once again, we won't mention what axis parallel rectangles are. You must know what axis parallel rectangles are. So this exact specification. And same for linear classifiers, right? So one point is important. So this is less than, so this is greater than or equal to 0. So the equality is part of 1. Okay, so this is a convention. Of course, you could also say greater than 0 is 1 and less than or equal to 0 is 0. But please remember that the convention is when W transpose X is greater than or equal to 0, we call that 1. Okay, we predict 1, otherwise it's 0. So these are some conventions we will avoid mentioning during the exam. You have to note that this is the case, and unless we explicitly specify, there is no bias. Okay, so for example, this is W transpose X greater than or equal to 0 and not W transpose X plus B greater than or equal to 0. If there is to be a bias, we will mention that explicitly. Okay, if we just say hypothesis class of linear classifiers, you can assume that they pass through the origin. Okay, so those are conventions that you have to remember. Yeah, so this is like very wordy slide, so I've just taken from my notes. Main point when it comes to questions on VC dimensions, right, in the exam, of course you need to know the definition, but please understand this is the approach, right? So this player one, player two game theoretic approach is probably the best. So two key things to note, which are very easy to get confused. Okay, player one has complete control over the geometry of the data points. Okay, so please note this. You as player one, always you have to imagine yourself as player one first, right? So player one starts the game. It is under your control. Okay, where which points you choose. Don't choose an impossible configuration and then argue that uh, these points can't be labeled arbitrarily, right? So no, so you have control over where the points should lie. So all that you need to do as player one is choose some m points. Okay, they could be anywhere, but it is your choice. And all that you need to do is show just one such configuration. Okay, so as far as player one is concerned, the configuration is under his control, and he only needs to specify one configuration of the points. Okay, I hope this part is clear. So it is players two's headache to label it this way, that way, and break it. Okay, the shattering you don't need to really know, but if you can Google this or Gemini, Chat GPT to understand. It's a very nice explanation should be provided what it means to shatter, but the idea is choose m points so that every possible labeling can be provided by h. That's the idea for player one. Okay, player two, of course, should work in the other direction and should try to break your configuration. So see, when it comes to these questions in the exam, right, there are two steps that you need to do. For a VC dimension question, if you're asked to find the VC dimension, there are two steps. One is to show that M points can be chosen by player 1, and to show that M+1 points cannot be chosen. Meaning, so I hope you get what I'm saying. Let's say the VC dimension is 30. Okay, just for example, of a hypothesis class is 30. So you must be able to show that as player 1, you can choose 30 points. Okay, that can be labeled in any arbitrary way, and still there shouldn't be anything going wrong. Okay, that you have to show. You are not done with that. All that you have shown then is the VC dimension is at least 30. Okay, if you want to complete the entire argument, you have to go become player 2 and show that 31 points, no matter what 31 points you choose, there is no classifier which can perfectly classify that. Okay, so there are two parts to it. Now, the first part is easy in a sense. The second part is hard. So what I would suggest is, let's say you are able to go till 30 and show that 30 points are 30 points can be perfectly classified. Let's say you try to show that 31 points cannot be classified. Don't break your head too much. You should stop at that point and enter the answer as 30. Okay, because if you start trying to think of the second argument, the argument from player 2 standpoint, that could be hard sometimes. Okay, so did you get what I'm trying to say? These two parts to the argument, and the first part is kind of easier, but if you want to complete the proof, the second part can be slightly tricky. So let's say you spend 4 minutes trying to argue as player 2, and you are finding it very hard to show that 31 points can also be shattered. Stop there. So just output the value as 30 and move on. Okay, so that is one point regarding VC dimension questions, which I would like you to remember. Okay, apart from that, this is all standard. So what happens for interval, axis parallel, linear with bias? So all this you must know. I'm not saying anything new here. So that is done. Right. So the final part regarding hypothesis, infinite hypothesis classes is you have a similar result for generalization error. Okay, so the result here is slightly different from what is given in the lectures. So in the lectures, it's some d log d by epsilon plus log 1 by delta. So in the textbook, apparently there is a tighter result, which is like linear in d, but you don't need to remember this. Okay, you need to remember the one for finite hypothesis classes that you must very much that you must very much remember. This one you can, if you don't remember this, it's fine. Okay, but I hope that's clear. So a similar result holds for infinite hypothesis classes with finite VC dimension. So that is, and you have a same sample complexity here. If you have a minimum number of samples as given by the sample complexity, then the train error will be close to test error, even if the hypothesis class is infinite. So that's the main idea. Okay, so that is done. What else you have? Yeah, so once you finish with the generalization error, you're completely done with the generalization error. Okay, so what you really conclude from there is the most interesting hypothesis classes are those having a finite VC dimension. Okay, so that is your conclusion from that. And for all such classifiers, the train error is a good proxy for test errors, provided you have enough number of samples as given by the sample complexity. So that part is done. So then you come to estimation error. So remember that estimation error is how close you are to the best possible classifier in your hypothesis class. Okay, and you are only dealing with the test errors. Okay, so you're only dealing with RD on both sides, but you have to specify some algorithm. Only then you can start talking about estimation. So why is this called estimation? So you can think of some parametric setting, let's say logistic regression. Okay, so logistic regression, the set of all logistic regression classifiers are what? They are just linear classifiers, right? So in some sense, so they're controlled by a parameter a parameter W, which is the weight vector. So what are you doing essentially is you're estimating W. Okay, you can see it as an estimation problem. That's where this estimation error comes from. Okay, so what you're doing with the learning algorithm in place is you're estimating, right? So in regression, for example, you are estimating the weight vector. In any other SVM, you're estimating a weight vector. Okay. So if you think about your classifier as some parametric form, okay. So the algorithm of choice here, as Prof already mentioned, is the one which minimizes the train error because that's the only thing we have handle over. So what he then goes on to show is that the estimation error can be bounded by the generalization error, okay, for the same hypothesis class H. And whatever you have done before holds true. So this, remember, whenever you see this RS minus RD, that is generalization error. Okay. So what we have managed to do is what all that we have proved before concerning finite and infinite hypothesis classes with finite BC dimension, all that can now be carried over, and we can show that the estimation error is also bounded. Okay. Or so the test error of your ERM is close to the test error of the best possible classifier. So that's what we have shown. Okay, so if you look at statistical learning textbooks, you will notice that this is closely associated with the notion of what it means for some class to be learnable. Okay, so this is called packed learning, or probably approximately correct learnability and all that. So if you are interested, you can go back and look at packed learnability, and that has to do with what is called the estimation error. Okay, so that is that. And you must know how to compute the ERM, by the way. So remember, you are only looking at the train error of classifiers from the hypothesis class. Okay, so that is main thing here. Yeah. So finally, with regard to these three errors, right? You start looking at approximation error. So this is a diagram that is kind of useful to understand the trade-off between estimation and approximation. Okay. So think about this rectangle or square as every point here is a hypothesis. Okay. So the square is the set of all hypothesis classes. So it contains every single hypothesis class you can think of. And H star is your base classifier. Okay. The red point is your base classifier. Now this ellipse is the hypothesis class H1. Okay. It contains all classifiers that come from H1. Okay. So that is the ellipse that you see. The green point, H star subscript H1, right? This is your best classifier from this hypothesis class. Okay, so this is the RDH, right? What you see on the right hand side of your this part. So this is the base error. Sorry, the error of this classifier, or rather, this is the error of the green point. Okay, if I can put it that way, the green point's error is what you see there. Okay, I hope this is clear so far. So this is the base classifier. This is the best possible classifier from the hypothesis class. Now what you are doing is you're solving an estimation problem. You are trying to find out the classifier from H1 that minimizes the empirical risk or the train error. Okay, and that turns out to be HSER. Okay, so far is this clear? The blue, green, and red points. This is the only new thing in some sense I'm saying. All the others are kind of we have already seen. Okay, so this wavy line that you see, line segment, is what is the estimation error. Okay, so you can think of, so what are we telling? If you go back to the estimation error, this is what, how far away is the test error of the ERM from the best classifier, right? That is what this is. So this is like how far away ERM is from the best classifier inside this hypothesis class. Okay, this double wavy line segment, it should be clear, right? This is your best possible classifier overall, base classifier. Therefore, this is your approximation error. Okay, so how close is my green point from my red point? Okay, this is for H1. You can think of H1 as, let's say, a neural network, a shallow neural network with, say, 2 layers, okay, and 100 neurons from each layer. So that a set of all neural networks which have 2 hidden layers, 100 neurons in each layer. That could be H1, for example. Okay, practically what we do in a machine learning problem is we start with some network And then we usually increase the model capacity, right? So because you want to see how far you can push your model. So you start in a deep learning setting, it will be a deeper network. So you move to H2. Okay, H2 is what? H2 is, let's say, 5-layer network, same number of neurons. That's fine, but it's deeper, having more number of parameters. So clearly it has greater capacity. Okay, that capacity is captured by the VC dimension. So H2 has a larger VC dimension than H1, and in fact H1 is contained in H2 because a 2-layer network is kind of, you can think of it as a sub network, or rather it is also contained in a 4-layer network, right? So if you set the last two networks to identity weights or unit weights, then you can kind of recover this 2-layer network, right? So this is strictly contained inside the bigger classifier, the bigger hypothesis class. Okay, so now what you're trying to do is same process you're repeating. So now what happens, because you have a more complex classifier with greater capacity, the best possible classifier is going to be closer to the true base classifier, right? Or so the approximation error is going to go down. Okay, because you have entered a more complex classifier, there is greater modeling capacity, right? So it's inevitable that the approximation error will go down, but it comes at a cost. The cost is the estimation error is going to increase. Okay, so why does this happen? Remember that this happens because you have the same data set S. So remember that S doesn't change. So you are not changing the data set. You're only changing the model. You're only going to a deeper model. So from conventional traditional machine learning, you know that if you keep the data set the same, but you increase the model complexity, you are going to need more data if you want to see the same kind of results. Correct? So if you keep the data set fixed and you only expect and you go for a bigger model, a more data hungry model, what's going to happen? You're going to overfit, right? So you're going to overfit. So what the estimate that you have for your classifier is going to go far away from your optimal estimate in this hypothesis class. So if you want to put it in another way, the sample complexity is a function of the VC dimension. Okay, so if your VC dimension increases, the sample complexity increases. So meaning for getting the same generalization bound. So if you want your train error, you can replace HS with HS ERM. If you want your train error to be close to your test error with the same tolerance level, you need to have more number of samples. Okay, so if you stick to the same number of samples and expect the same bound, you're going to be disappointed. So which is why the estimation error goes down. So you may think that I'm arguing with the help of generalization error, but notice that a few slides back, what we have shown is, when did we show that? Yeah, this is where we showed that, right? So the estimation error itself, the bound for that we showed using the generalization error only. Okay, so all these things are kind of related. Okay, so long story short, there is a trade-off between these two errors, and as you increase the hypothesis class, the complexity of the hypothesis class, the even though the approximation error goes down, it is going to come at the cost of your estimation error. Okay, so yeah, so that is regarding these errors. So SRM we don't really test in the exams because Prof also has not discussed too much on structural risk minimization, so that is kind of ignored. We will not discuss too much about that here. The final part that is there for the exam, apart from the privacy part, is sample compression. Okay, so again, I'll let you read this later. You already know this. So what you have to note here is you have to note the following. So your data set S. So when you're looking at things from a compression standpoint, S is generated using, or rather S is labeled using the hypothesis class. Okay, so it is not some arbitrary data set. So what is fed into the compression decompression procedure is not some arbitrary data set. It is a data set which has been labeled using classifiers from H. Okay, given that, can you compress it is the question. Okay, so compression is not with respect to some arbitrary data set. but data sets labeled using H. That's the first point. The second point is this is an upper bound. Okay, so K. So meaning it's the you need at most K points. So or rather, how many points do you need to retain in the worst case? Okay, it could so happen that you need to retain only 3 points for some specific scenario, but then there might be a worst case situation where you need to retain 5 points. Okay, so you have to be careful about that. So you have to return the value of K that you return has to be the maximum value that you need in the worst case situation. Okay, so for example, this was again asked in the group also, right? So this is one sub case of your compression algorithm. There are at least two other sub cases I can think of, right? So when all of them are positive, for example, then your if else block, what it should have is what you could do is you could return the rightmost point. So for a moment, assume that all of these points are green. Then there should be a subclause in your sample compression algorithm which says, output. Fine. Okay, so if all of them are green, it will still work because you can take the rightmost green point and the leftmost green point, and that will still work. So in that case, it will be green here, green here. But corner case could be all of them are red. Okay, so for a moment, assume that all of them are red. So in that case, what should you do? So your algorithm will fail, but that doesn't mean sample compression scheme is wrong, right? So it just means that your algorithm has been specified incompletely. Okay, so what we did in the lectures is an incomplete specification. You have to be careful about that. So the statement is still valid. So if all are red, what do you think will happen? What clause can you add? Uh, so maybe take the farthest point, and then the classifier you return is something like this. Okay, so there you only need 1 point. Do you get the point what I'm trying to say? So let me draw it with a pen here. So let's say your data set is having 1, 2, 3, 4, 5, 6. Okay, on a line. So I've assumed that there is a dotted line going through this. This is the data set you are given. So this will pass through your compression decompression routine. And what you can do here is in the sub case, it is enough if you know what is the rightmost red point or the leftmost red point, because then what you can do is you can say that my classifier is going to be this plus some epsilon. So for example, this turns out to be 5. Okay, the value of this data point turns out to be 5. Your classifier can be 5.1 to let's say 5.3. Okay, H interval 5.1 to 5.3. Excuse the drawing. So the value of K that you return in this case is 1. It's enough if you know only one data point, but then that doesn't mean sample compression scheme is 1. Okay, it is still 2, because in the worst case scenario you need at most 2 points. Okay, is that point clear to all of you what we just discussed, what I just said? For considering all possible scenarios where what can happen to the sample compression scheme. Okay, so that is
how it is related to decompression, sir? I didn't get that one.
see, compression, what do you compress? So how do you compress? In this scenario, understand, right, what compression is. You look at the data set, and let's say there is an if condition which says that okay, so let me go back here. I'll write it down. I anyway have access to this. So in the notes, this is there, right? So see, you can think of cases. So you have to write two algorithms, right? You have to write a compression algorithm, and then you have to write a decompression algorithm. So what is the compression algorithm? The compression algorithm is a function of your data set, only your data set, right? And also in fact, that is all right. You only need to take the data set as input. So what I will do now is I'll ask the following question. So if all, or rather if yi equal to 1, okay, for all I, let's say there are 1, 2 mod s, right? This is the number of data points. So yi equal to 1 for, or rather 0, right? The case I'm interested in is red. If all of them are red, what should I do? Okay, what? So I have to return, in each case, I have to return a subset of points. So let's say T is the subset. So what I will do is I'll take max over xi, or rather max over I xi. Okay, I'll call this, let's say, some x dash. Okay, this will give me the maximum value of the x coordinate of all the data points, and I'll return the I'll return the point as, in fact, I'll return this. Yeah, but what do I need to return? So once again, what does your
Can I just try to
compression
explain it once?
yeah. So what does the compression return? It returns only the subset. Okay. So this part you're telling me, is this part what you're asking me to, Anupam?
No. I was saying I can give a simpler example if that helps, unless you want to show the algorithm.
Okay, yeah. So I just maybe go with the example alone. So yeah. So I'll take this. So assume for a moment that all of them are red. Okay. So let me turn the whole thing red for a moment. Okay, the line will also turn red, but that's fine. Yeah. So what do you do in this case? So this is one subcase of the algorithm. What you have to do is you have to compute the maximum of the x coordinates of all these points and return, or rather return the rightmost point. Okay, if that makes sense. So the compression algorithm here will return, okay, or rather rightmost point, or the point with the maximum x coordinate. You can think about it either way. So it will not return just the point, right? When I say it return the point, it will return x comma y. So what will the
You don't need
decompression?
the right, in this case, you don't need the rightmost point. You can return any interval. It's okay.
Agreed. Yeah, you can return any interval, but it's kind of easier to say, return the
Yeah.
rightmost or leftmost, right? So, so that's the compression algorithm. That's what it's. So it's going to return what? X max, uh, comma 0. Correct. In this case, that's what it'll return. In this case, it is going to return 2 points. So return the 2 green points farthest from each other. Okay. So it is going to return 2 points. So T, this will be T. It will return a set, by the way, right? It's going to return a set. So it's a set of points. So here it will return what? Say some x11, x2. It's for the sake of simplicity, I'm just calling it x11, x21. Okay. This is what it will return. Okay. So what other cases are there? All green will anyway come in here because there is no point, there's no problem there. If there is exactly one green point, you have a problem. Okay. So you can't use this rule here. So that would, let's draw that scenario that maybe we can just delete this.
But
Delete.
sir, when we will be doing decompression, so if there are all the points are green, then it is, we can make the maximum interval as the last points, the farthermost points. But what happen if when we decompress it, the new points can come beyond that? So how do we will classify them?
Sorry, can you repeat the question? I didn't get it.
As Sir, I was saying about if all the points are green,
All the
let's
points are
say
green.
like 4 points in the last row, all are green, and if we make an interval from first point and the
10
last
o'clock.
point,
See,
first
all the points
point,
are okay. See, there are 3 cases we are considering, right? So some 2 points. So,
What she's asking is what happens if a new point comes in? If all points are green and then another point, you have defined the interval and then a new point comes in, what are you going to do?
why? So see, that case won't arise, right? So you are only dealing with S. See, what is the idea? Let's say you are dealing with S, right? You're not dealing with multiple data sets at a time. All that you're asking is, if you are given a data set S, can you compress it and decompress it in such a way that the labeling is still preserved with the smaller subset? Okay, so okay, let me realize the situation that you are asking. All 4 points are green. That is S, right? So S is the set where you have 4 green points. Is that correct?
But sir, we take sample in compression, and in decompression, all the points we have to consider. Like Professor said, 1,000 points. We are taking 10 points, and we have classified them correctly. So it should classify all the rest of the points also
Correct.
correctly.
Correct. Yeah.
So,
All the rest also have to be classified correctly.
so in this case, when all the points are green, how it will classify rest of the points correctly, because it will bound the interval from first and the last, so it can, the rest point can come beyond it. This,
See, you can't introduce a new point, right? See, what is this? The idea is, can I compress a data set given to me? Okay, that is all. That's the question. So you're only dealing with one data set at a time, right? You are not dealing with a new data point that you inject and suddenly make the data set different. Okay, so what are we saying? I have S with me. I am going to pass this through a compression algorithm. What is that compression algorithm going to do? It's going to throw away the middle 2 points, and it's going to return this set of points as T. Okay, it's going to return T. Now a decompression, so this is compression, right? So compression will return T. Now decompression will take T as input. And what will it do? It will return a classifier which says start. So uh, where is this bracket? So start with this, okay, and end with this. Anything that goes in between is green. Okay, now you're asking, what if there is a red point that comes in between? Is that correct? Did I understand your
no
question
sir,
correctly?
like red point cannot come in between here,
Okay,
but what if the green points come out of this interval?
that is also something which can't happen, right? See, you are not worried about some
I
other
think
data set.
I think one core thing here is she's thinking that there are new data points getting generated.
Correct. Yeah,
Okay.
yeah,
No,
you're right. Yeah,
Yeah.
right.
let
So see,
me,
there are
let me
no. Yeah,
no,
yeah.
what happens is very simple, Ravina. The example that the professor has given is 1,000 points are there. In that 1,000 points, considering the entire set of 1,000 points, what is the minimum number of points that are needed to define an interval that can classify all 1,000 points? So if all 1,000 points are green, then you just need 2 points to classify the entire interval, the leftmost and the rightmost point. Okay, so
Right.
in all cases, you're considering all 1,000 points in one go. You're not taking like 10 points and then 20 points and 30 points. That's not what the professor was saying. He was saying to classify those 1,000 points, you need a minimum 10 points. But that minimum 10 points is classifying not just those 10, you're classifying all 1,000 points based on those 10 points. That's what he was saying.
Yes sir, I got it sir.
Okay.
Okay.
Nice. Okay. So yeah. So that is what you have to be careful about, right? So you have to come up with different cases. So in the first case, this is the most common case where you have at least 2 green points, and this will also include the case where there are only green points. If there are only red points, you could, for example, return the maximum and the corresponding label. If there is only one green point, so here also you have to be a bit careful. You have to return at least 2 points. You can't just return one green point alone, because you don't know how close the red point is going to be, right? So if you want an interval, you need at least 2 values. So you have to be careful. So here also you return the green point and maybe the point to the right of it, okay, and the point to the right of it. Of course, you could then ask, what if the data set is like this? There is nothing to the right of it. So I hope you get the idea, right? So there are several subcases that you have to think of when you are drafting your compression algorithm. But the upshot is, whatever you consider, you need only 2 points. Okay, that's the worst case. So you don't need 2 points for sure. And that is the sample compression scheme, the size of the sample compression scheme, right? So it is size 2. Okay, there may be situations where you need only 1 point, but that doesn't mean that it is size 1.
So
Okay.
there was one thing that the professor had mentioned. Maybe I'm misremembering it. So in the earlier part of the lecture, he mentioned that the sample compression size of the K is at the most as much as VC dimension D. Then later on, he said that it has not been, there's a sample compression conjuncture which has been not been proven that D is equal to K at the most. So which one is it? Is it not proven, or is it?
Right. So there are
No,
two.
I think he was saying in one direction relationship holds,
Correct.
not in the other direction.
Yeah. So sample compression.
Yeah, I'm confused of which direction.
Yeah. So sample compression implies finite VC dimension. This has been proven, but finite VC dimension, we don't know. So the hope is it implies sample compression, but we don't know if it is. We don't know if
Okay.
this is
Okay.
true or
Thank
not.
you. Yeah. Thanks, Lavina. This was confusing me a bit. Okay. I can see it properly now.
Right. Yeah. So yeah. So that's all I also had. I don't think there is anything else here. Yeah. That was the last slide. So yeah. So all formulas in this week, in the last 4 weeks, unlike the first 6 weeks, right? So I'm going to say, in fact, I even take back what I said about this particular formula, right? So where this logarithmic dependence, where was that generalization and uniform error
Yeah,
for?
this one, this one. Yeah, this
Yeah,
one.
yeah, this is important. Yeah, this is very important. But this part also, right? Please memorize this also. Where is this? I keep going. Yeah, this VC dimension. It's not too hard. So of course, he won't ask you numericals on this, right? So he won't ask you to solve anything, but better to remember this one also. So I take back my statement of not remembering certain formulae. Please make a note of everything. It's only 4 weeks, right? So 7, 8, 9, 10. And 11, I am not discussing because, yeah, it's like we are not like going to test you. We are not grill you. We're not going to grill you in that part because there are no graded assignments anyway. So it's like the last 11th week. So nothing much there.
Now, can we start asking the important questions now?
Important as in?
How many questions are going to be there in the end term roughly?
Roughly around, I think we have 15 odd questions, if I remember.
It is not bad.
Last time it was 13. I think last time it
Right.
was 13.
Maybe slightly more. There will be one bonus question, okay, which will say 0 marks. It will be for 0 marks, meaning it's like you won't be penalized if you don't attempt that question. So there will be a, please watch out for 0 marks and a bonus. We have also mentioned, I think, the words bonus clearly. We haven't decided what to do with the bonus question, right? Whether meaning what weightage it has in the end term, right? So that part we'll let you know, but before itself, I'm letting you know that it's a bonus. It's counted for. It'll appear somewhere in the grading final T score, right? So what
So the 0
exactly?
marks and bonus is different, or is it same?
No, it's the same thing. So meaning,
Okay.
so there is a bonus component, but it's just that those who are not able to solve that should not. It's fine.
Worried.
Yeah, 100 marks. So it's not a part of the 100 marks of the end term exam. But then, if you manage to solve it correctly, you will be given additional credit somewhere in the T score. We haven't decided where.
Okay.
And what about like heavy numericals from weeks 1 to 6? Like
No, weeks 1 to 6, heavy numericals you won't have.
Like the cuts, the L
No.
equal to D max.
No, you won't have. So it's the focus is more on.
Because I've completely forgotten I was trying it this today. I I could not solve it.
In the last term, the first few weeks questions are mostly about some formulas, MCQs kind of things.
Correct. Yeah, you can expect something similar. So we wanted to test the last 6 weeks only mainly, meaning or more than last 6 weeks. The stats learning part is what we mainly focus on.
And in fact, there were 4 or 5 questions on the VC dimension alone.
Right, right. Yeah. So that's about it, I think.
Any numericals on week 11 kind of a thing?
So week 11, I can't say much there, but it's yeah. So as long as you know, you must know the formulas, formulae, whatever. So whatever is mentioned there, especially so mainly you can randomized response is the main thing. Okay. So Laplace mechanism is it's also a part of the syllabus, but randomized response is what we are mainly testing in the exam.
Okay.
So you can focus exclusively on first lecture of week 11. That is also fine.
Okay, not differential. Okay.
Yeah, that part. Yeah, not really because yeah, we should do a graded assignment soon. At least next term we can start testing it properly.
Yeah, please, if you can, in fact, give weekly graded assignments for the next batch, assuming they don't blame me for it. I think it might be beneficial.
Right.
It gives more practice to people. That's it. It's not about, what is going to come in the exam, but just allows people to test their concepts a bit. I think that I'm struggling in week 11 for that.
But actually, these questions are not trivial. So we have to consider that also because it requires a substantial amount of
Yeah, I agree. I
effort.
agree, Ravi.
Yeah,
Completely.
I think this 2 week thing is quite good. It's only for the last 2 weeks that some special arrangement has to be thought of.
Right.
Otherwise, yeah.
Yeah. So that's
Sir,
all I
when
have.
are we going to get our PA
Yeah. So
marks?
yeah, tomorrow only we have to start. We haven't started, so we'll try to finish as soon as we can.
Is
Will we not get before end term? Because I need that to stay like,
it's now 2 days only, Anupam. It's only 2 days. You cannot build any more strategy.
morale boosting is needed.
Yeah, we'll see. We'll try to. We'll try to. We have
Yeah.
to start. Yeah, that's the only pending thing for this term. So we'll try to finish it by as soon as we can. So we'll try.
Overall, in this batch, in this term, how has been the performance? Is it good or bad? Like you're giving some bonus question in the end term also. That kind of indicates that the batch has not been doing good, and you're helping all of us.
No. So this batch actually it has been decent. So I thought quiz one would be very bad, but it ended up being very good. In fact, so at least the average performance, right? Not
Okay.
individually, I don't know, but in fact, I think it's even better than last term. So
Okay.
yeah, the bonus question was more of that idea was mooted, and we felt it was. In fact, we want to introduce it in other courses also, right? So it's a nice,
It's a nice thing. A nice
yeah,
concept.
yeah. Preetham, I think Preetham is who added it in the group, right? So I think it's more of not to. It allows us, gives us an opportunity to ask questions which we would otherwise shy away from, right? Because it's hard or students will suffer. So all that baggage we can remove at least for a few questions once in a while.
Yeah. And it will also give a chance to some students to differentiate themselves, those who have gone beyond the regular way of thinking, and they can, excel and answer such questions.
Right, right. That is true. Yeah.
So just one more question, Karthik, just
Yeah.
in general, to reorient myself properly. Like you said in quiz one, that it was tougher than the last time's quiz one. Similarly, if you look at the end term, where do you think the difficulty level lies?
In term, see, the challenge will
Term
be
to end
the
term. End term to end term.
in term. So
Like last time, you were very clear, right? The quiz one is tougher than the quiz one last time, which was true.
I
It
don't
helped
remember.
us reorient ourselves. So I'm just asking for
It
this
was
time.
actually very helpful. That guidance
Yeah,
was very helpful for us. That made all the difference.
yeah,
Okay, so I
because you
don't
put in more
exactly.
effort.
See, let me see. I have to take a look. I forgot. I only remember a few questions from last term. Let me see. It was shared in the group, right? So
Yeah, it's there in the G space if you want to have a look.
yeah, algorithm CDS. Let me see. Okay. Okay. So from what I notice, either on the same level or maybe marginally harder. So I won't say it is easier than last term, but it's not like 2 times hard or nothing of that sort, right? So it is like slightly harder than last term.
Okay.
What I would say, if you have seen the last term's end term paper,
Yeah, I have. I mean,
yeah,
most of us also.
yeah, I think maybe slightly harder than last term,
Okay.
but not like the way I feared for quiz 1. I don't think it will be as hard as that.
Oh, that's good.
But that was very helpful, sir. But the session that you did for the quiz 2 and all the inputs you gave, because we all got oriented that we need to move up a little bit in terms of what kind of questions we expect and how do we have to solve it. That was helpful.
Yeah,
Right,
for me, the biggest takeaway was, you saying that it's going to be tough. That was enough to get things moving.
right, yeah.
So your notes have been very, very helpful.
Yeah.
And your sessions that you have been conducting, I mean, I did not attend the regular live sessions, but quiz 1 revision and this end term revisions, really wonderful. You are a great teacher. Wonderful.
Thank you very much. Yeah, thank you. Yes, Sahiti, you have a question?
Yeah, so I just have a clarification regarding the generalization error.
Okay.
Is it okay if I ask that?
Yeah, please. Yeah.
So, in the previous question paper, when I was going through one of the questions, we had to calculate the ERM and then we had to calculate the generalization error, and then the training error was 0. So, when we're finding the true test error, to subtract. We didn't have the PMF for all of the points. They were only gave it for one of the points.
Yes, that's true. Yeah.
So in that situation, then like what would happen if the other points were classified incorrectly? Like how do we calculate the test error? I think I'm a little confused on that.
Okay, yeah, 1 second. Let me pull up that question. So, this is the question, right? You had.
Sir, can you please share the screen?
Yeah, I'm just pasting that. Pasting that particular. Okay, so what did we ask here? 0, 0 belongs to class 0.
Just this.
Class 0. So this is red, green, green, green. Okay, HHS ERM is. Yeah, so yeah.
There was one where we're just adding up x1 and x2, and if it's greater than theta, h star is 1 and then 0 otherwise.
The ERM, right? So this is the linear.
Yes.
So the hypothesis class is linear, right? In this case, is that
Yeah.
that the hypothesis class given?
The hypothesis class is not necessarily linear, it's just we're adding the x1 and x2.
Okay, x1 plus x2. Okay, yeah, x1 plus x2 greater than or equal to theta. So, this, yeah. Okay, so there is some more data I missed out. Once again, let me add that also here. So this is the complete data, right? So this is, yeah, this is the question. So you have priors 0.5 and one entry in the class conditional density each is given. Yeah, so your question is P of y 0, 0 given y equal to 0 is 1. Only for this point it's given. Is that the question for each case?
Yeah, because when we're computing the true test error in the generalization error, we're taking the incorrect values, right? So for here, p of 0, 0, the actual value given is the red point, which
Right.
is y equals 0. And so in the computing the error, we take it when y equals 1 and then multiply that by the probability of y equals 1. And then we do the same thing for the other points too, right? So, but the other points are not given in the PMF.
So the reason they are not given is the indicator will be 0 for them. So, right. So for example, see, you have to, I think without solving the entire thing, we can't. So you're talking about the test error, right? The generalized base error. Is that the one you're talking about?
Yes, the
Okay.
generalization error.
The wait once
Well,
again.
the test error as part of the generalization error,
Oh, the
because
test
the train
error.
error is 0.
Okay. So you're talking about RD. So you're talking about RD of HSERM. Is that correct?
Yes, yes.
Okay. So you're talking about RD of HSERM.
Mhm.
So HSERM is, by the way, what this x1 plus x2 greater than or equal to 1. Is that correct?
Yes.
Okay. So HSERM is in this case is is equal to 1 if x1 plus x2 greater than or equal to 1, which would mean wait, greater than or equal to 2, right? Isn't it 2?
It's
No,
one.
Uh,
because
wait.
only 0, 0 is classified as
Yeah,
red.
it's 1 0 and 0 1. So that's a line which is going diagonally.
1001. Sorry.
Yeah, 1 0 0 1.
Wait one second. Am I missing? So what will this line look like? Passing through
From
this,
there, yeah,
right?
from 1
So
0 to 0 1. Yeah.
okay. Sorry, I'm
Or 0 1 to 1 0. Yeah, 0 1 to 1 0.
right. So I'm thinking of the label and adding
Yeah.
1 and 1 and making it 2. Sorry. Yeah. Otherwise, it is yeah. So this is ERM. So RSHS ERM is 0, as you said, and we want to find out RD HS ERM. So see, the point here is the way we constructed this was you given grid, right? So given y equal to 0, the only point that can come up is 0 0, right? So 0 0 can be the only red point. Is that clear from the probability that you see?
Yes.
Right. So the only red point that the distribution can generate is 0 0. So there is no, it's like deterministic. So 0 0 is the only red point. Therefore,
Okay.
so therefore, when you calculate the test error of the ERM, when you're expanding the expectation over y equal to 0, it doesn't matter what these three are anyway 0. The probability of x given y will be 0 for these three. Is that
Yes,
correct?
I got it. I just missed that part
Yeah.
because probability of 0, 0 given y equals 0 is 1, which means that
Everything
all of
else
the other
is
points is 0.
0. Yeah. So
Yeah.
that's why we purposely ignored the other three so that you can infer that the rest are 0, and so that's kind of added to confuse so that you start looking for the other things, but then you have to realize that this is 1 and therefore other three are 0.
Okay, got it. I was confused. Thank you.
Yeah. Okay. Yeah. Anything else? Any other question? If not, we can.
No, sir.
Okay, great. So, yeah, thanks for joining. I hope you had somewhat decent ADS this term. We'll see what happens after the interim. So we'll try to share the scores for the programming assignment soon. Okay.
Thank
All
you,
right.
sir.
Thank you.
Thank you, everyone. Yeah, thanks a lot.
Thank you so much.
Sir, this document Notes? Can
This
you
I
share?
will I will upload now. I will upload it
Okay.
in that same slides folder. I will upload it there.
Okay.
So the notes are also, see, a few things in the notes I have changed. For example, there are a few parts which are incorrect. So for example, the factor of 2 in the factor
Okay.
of 2
Yes.
here.
Yes.
Okay, so all these things I have updated, and also the statement of uniform convergence here, the statement of uniform convergence for this case. So these things I have updated. So kindly take, if you have followed this,
Okay.
please take a look at it.
Okay.
And also the slides, right? You will be sharing the
Yeah,
slides you were using today.
Yeah, I'll same slides folder I'll upload along with the notes.
Okay.
Okay.
Thank you. Thank you so much.
Thank you.
Thank you, sir.
Yeah, thanks.
Thank you, sir.
Thank you.